Okay, then let's continue with statistical methods. So we are in the process of discussing PPI, so psychophysiological interaction analysis, which, as we briefly introduced last time, are one of the ways to study cognitive process-dependent connectivity in the brain. And as we also at least mentioned, is that they are a variant of GLM designs, and more specifically they are ANCOVA designs. And since they are ANCOVA designs with interactions, so not additive but ANCOVA designs with interactions, hence psychophysiological interaction, we decided, or I decided, that it would be good to first look at how ANCOVA designs with interactions are actually formulated in terms of GLMs, and to get to that, it makes sense to, before doing ANCOVA, discuss how ANOVA and two-way ANOVA are actually formulated in terms of GLMs. So then you also learn how these are formulated, and it's much easier to understand PPI designs from this perspective. And we did a little bit on one-way ANOVA. So we basically established that the fundamental model for data points are Yij, where I is the group membership or the level of the experimental factor in a one-way ANOVA design, and J is the number of the data points within a group that the one-way ANOVA model from a GLM perspective refers to a normal distribution, univariate normal distribution over this data point with a group-specific expectation parameter, and this group or level-dependent expectation parameter, I think we went up to say, okay, this should be given by some offset plus the group-specific effect. Yeah, so that's offset, and that's the group-specific effect, group effect or level effect. It's just for one-way ANOVA designs, one usually thinks of different groups or different conditions. The important thing the whole time is that we assume that the error contributions in this structural form of the ANOVA GLM, that these error contributions are independent. So we're not talking about repeated measures designs essentially, but cases where our experimental units are modeled using independent random variables. So error contributions are independent. That's an assumption that's going on throughout everything that we do. Also when we get to PPI at one point. And then we discussed that this kind of structure model in its GLM form takes on this form where we stack all the data points for, let's say, 3 groups below one another. Of course, one can make this more general by not looking at 3, but let's say K groups or whatever. But I think not that much is earned by this level of generality. So we have our data vector as in a standard GLM, and then we went on to discuss that our beta parameter now has our mu0, our alpha 1, alpha 2 and alpha 3. I think we did 3 groups, and that we can basically create this expectation parameter vector by multiplying a design matrix that has ones for the offset, and then group specifically ones and zeros where they should be. So essentially getting something that roughly and with some imagination and so on looks like this. So you have kind of these ones on this kind of diagonal. Does that make sense? Yeah, it's 4 and 4. And I think this is what we went up to, and I then said this is over-parameterized, but we didn't really then did more with that. So with this over-parameterization and GLM designs, one could, so now that I'm teaching that for, I don't know, the fourth or fifth time with this over-parameterization, thinking of one could also not first always discuss the over-parameterized form and then introduce the normal form. I'm looking a little bit for the additional benefit of introducing this over-parameterized form, but maybe we see that clearer if we go to the two-way case. Here, the problem is as follows. What we essentially have is that we want to predict our mu1 based on mu0 plus alpha 1, mu2 based on mu0 plus alpha 2, and mu3 based on mu0 plus alpha 3. So we use 4 variables, so mu0, alpha 1, alpha 2, and alpha 3, to construct 3 values. Yeah, and essentially this is one too many. So let's see whether we can give an example. Again, this is I'm not prepared. It shouldn't be that hard actually. So let's say our mu1, mu2, mu3 are 2, 3, and 4. And one parameter, yeah, that's I think the easiest. One parameterization would be that we have mu0 being 1, and hence we have this. That means that our alpha 1 needs to be 1, our alpha 2 needs to be 2, and our alpha 3 needs to be 3. So that would be this. Oh, I think that's the easiest way to show this. Alpha 1 is 1, alpha 2 is 2, alpha 3 is 3. Now these mu i's of course can also be constructed using a different parameter combination, namely simply using mu0 being 0, alpha 1 being 2, alpha 2 being 3, and alpha 3 being 4. Then we can also, so that's one way to do it. Another way to do it is to get 2, 3, 4 by doing 0 plus 2, 0 plus 3, and 0 plus 4. That means we, if we are constructing these expectations of the groups, if we do it the way we did before, that we define an offset and we define an effect for each of the groups, then it's not uniquely defined how the values of our offsets and effects of the groups should be to result in a specific setting of the group expectations. Yeah, so there are, if you look at these here, these are the parameters. The mu I are just the result of the product of the design matrix with the beta parameter. The parameters, there are different parameter combinations that yield the same expectations. Yeah? Different way to see to think about this is that, of course, the group expectations model the group averages. Now, if you compute the group averages and you have 3 group averages, and then you want to map those onto 4 parameters, there are different parameter settings that could explain the group averages. Yeah, if you view this more from the construction of the model, then it's not a sensible construction to come up with essentially 3 values that influence the expectation of the data points. But these 3 values you can either create with this parameter setting, with this parameter setting, or of course with any other parameter setting where you subtract one number from mu0 and add this number to all the other ones. Yeah? Of course, there are even more. So I mean, you could also say mu0 minus 1 and then have here 3, 4, and 5 and so on. So the bottom line of this whole thing is that this parameterization where alpha I goes over groups, where R is a number of groups, is over parameterized and not good. So essentially one might also just not introduce that at all, and in the beginning introduce what is called the reference cell formulation. And the reference cell formulation, I think, especially when we talk about 2x2 designs, then it makes maybe a little bit more sense than it does right now. Here it just means that instead of modeling the expectations as follows, so instead of modeling things like this, one of the groups is referred to as the reference group. So this would be our mu1, mu2 in terms of our group expectations. And this reference group then is predicted by a single parameter, mu0. And alpha 1 is set to 0, so it's actually removed from the model at all. And our mu2 is modeled by mu0 plus alpha 2, and our mu3 is modeled by mu0 plus alpha 3. There is an important difference between these 2 things. So here, the alpha was the if you want, absolute effect of level I. So you could, if you want to imagine that in terms of error, not in terms of error bars, but in terms of bar graphs, if you, because I guess this is something that you're more familiar with, you think of, you have some data and things look like this in your 3 groups, so group 1, 2, 3. Then here the idea was there is a common offset to all of them. So this must be, because it's in all of them, must be something like this. That's our mu0 in this case. So in this case. And in addition to that, for the values, for the expected values or the averages of the groups, however you want to see it, you have these effects of each treatment. Now the difference is in the reference cell formulation is that it's a relative, so the group effects are now relative to the first group of level I for I larger than 1 relative with respect to group 1. Of course, one could use a different group. One doesn't need to necessarily use the first group as a reference group, but in general, it's easiest to use the first, and specifically if you go to more factorial designs, not to make it easy to not lose oversight, then the interpretation is different, because if we have the same data, so let me try to draw the same data again, the same data here, and this, then the mu0 is now the expected value of the first group, mu0, and the alpha 2 is the difference with respect to the first group, which, if it's an additional difference, is of course quite easy to see. So that's this, that's alpha 2. And maybe we should do that like this. And maybe with a different color. So that's now the alpha 2. So it's only the difference with respect to the first group, which of course looks quite different from an overall offset here. Then here, of course, if it's smaller, the alpha 3 is essentially what is missing here. It's also the difference with respect to mu0, but here it's of course a negative thing. Yeah. So why is this important? Because for example, if you use SPSS or whatever, if you look at the estimated effects, you should be clear about how to interpret them. So are these the differences with respect to a reference cell, or are these things that are added to some common offset? And it's in terms of one-way ANOVA in the GLM formulation, and in general, because it doesn't work like this, because it is over-parameterized, it's always this case. So if you then have some parameter estimates like mu0, alpha 2 and alpha 3, you need to be clear about that mu0 is the estimated expected value in the first group, and alpha 2 and alpha 3 are the differences between the first group and the second group, and the first group and the third group. Yeah. In terms of the GLM formulation, this means that we can actually do that here. This means that alpha 1 is constrained to be 0, so alpha 1 is left out of the whole thing, so alpha 1 doesn't show up. So we only have the parameters mu0, alpha 2 and alpha 3, which also means that we have to, of course, to have a proper design matrix setup, we have to remove the column that referred to alpha 1. Yeah? So now you see also at the level of the design matrix that here the columns, if the matrix is not ranked efficient, because you can add, for example, the second and the third column, and you don't get the first column. Yeah. So, which was the case previously, that you could use, that you could recreate a column by a linear combination of the other columns, which is always a sign for the degenerateness of a matrix. This is kind of the matrix way to speak about it. The overparameterization way to speak about it is to say that, as shown here, if you want to create predictions for 3 groups, it doesn't make sense to use 4 parameters for that, because these parameters could then have different values. Yeah? So this then leads to the common picture of design matrices for one-way ANOVAs that look like follows. So if you ever looked at a design matrix for a one-way ANOVA, you usually see something like this. Where these are just the ones. So this is a column of ones. Then you have zeros. Then you have some ones here. Then you have some ones here, and the rest of it is zeros. So here you have zeros. Here you have zeros. And here you have zeros. So that's zeros, and that's ones. See this? Yeah. So this is the typical appearance of one-way ANOVA designs in, for example, if you use SPM for second-level analysis, then you would see this. I don't know, do you see design matrices in R? Some people, I think, work with R. No. Okay. But everybody loves this linear mixed models stuff in R. Did you encounter that? Because in principle this is all based on design matrices, so I don't know what they did there. But yeah, so this is the typical appearance, and it relates to this reference cell reformulation of one-way ANOVA. Yeah, but then we have, once we have it formulated like this, we have a standard GLM of either this form or this form, and we can use, like we discussed before, Christmas and so on. We can compute better parameter estimates, which of course correspond to the estimates of the respective parameters, so mu0, alpha 2, alpha 3, and then look at our parameter estimates and look at the ratio of parameter estimates with respect to variance estimates, and do, for example, t-tests on the parameters or f-tests based on model comparison. Yeah, so that's one-way ANOVA in a GLM setting. If you want to relate this to the one-way ANOVA that rests on mean squares and sum of squares within and between groups and so on, I recommend this classical variance partitioning and f-test business in PMFN. You might want to look into what f values are in the T and F statistics section first. It's the same thing, but it requires some revision of certain things, and then one is there. But now I'm more interested in only the GLM setting, because PBIs, they are in neuroimaging, they are always in the GLM setting, so we don't want to go over the classical variance partitioning right now. Are there questions right now about one-way ANOVA? No. Good. So then the next topic is two-way ANOVA. So what do you remember about two-way ANOVA from undergraduate statistics? Can somebody tell me something?
Several factors influence dependent variable.
On the dependent variable, yeah. Yeah, exactly. So you have different factors, and what's going on with these factors? And can you say a little bit more? Because then I can drink something.
Yeah, it's like, as I just said, it's like one-way ANOVA, but with maybe like we have dispersion there. Yeah?
Dispersion.
So it's kind of that they sum up, and they have to be like this, like the parts should be like this one.
Mm-hmm. Yeah. Any other additions to that? So, what else do you remember about two-way ANOVA? Any terms? Any things?
Look at main effects and interaction effects.
So what are those?
So the main effect derives from one factor itself. You have two groups, for example. And the interaction effect is if the effect in one group is different depending on in which group you are in the other factor.
Yeah. Anything else from two-way ANOVA? No. So two-way ANOVA, of course, one can create higher order ANOVAs, so one can also cross more than two factors. So two-way ANOVA is the crossing of two factors. Three-way ANOVA would be three experimental factors. Important thing about factors is always, of course, that they have various levels. We've already seen that, of course, for one-way ANOVA, where we talked about the groups. I'm trying to stay with levels now for two-way ANOVA. Usually, one has some experimental factor. I have here this data set, which is it's an artificial data set, but it's meant to represent brain volume, and there are two factors, age and alcohol consumption. And then the important thing about the experimental factors is that they have discrete levels. So they usually have a name. So a factor could, for example, be alcohol consumption. And then they have a low or high. So then they have two levels, low and high. So whenever you read a paper and it's talking about it's using an ANOVA and it doesn't say how the factors are called and what the levels are, throw the paper away or provide constructive criticism as a reviewer and tell them that they should write down what the factors and what the levels are, because otherwise it's useless. Then you usually have more than, of course, in a two-way ANOVA you have these two factors. So let's cross this in this case with H, and then also have two levels. And then these designs are usually called 2x2 designs. If each of the factors, so this would be factor 1, if each of these factors has two levels, so you can of course also have two-way ANOVA designs that are 4 times 3 or 5 times 2 or whatever. This is usually what you get when you let people come up with experiments without any idea of what they want to do with the data. Then they come up with these, I don't know, 4 times 1 not, but they come up with 5 times 3 designs, of which they only measured certain cells, and it's all horrible. So 2x2 designs are nice because first of all they are quite easy to think about, or I mean they're definitely easier to think about than 2x3 by 4 by 2 designs, then it's also possible, and that's the nice thing about 2x2 designs, because you have essentially 4 cells for which you need to acquire data. So you have factor 1 and factor 2, and then you have the levels of each one, 1 and 2 and 1 and 2, maybe like this. And then you need to, of course, acquire data, so data points for each, if you want to do a proper job, acquire data points in each of these cells, and ideally you acquire the same number of data points in each of the cells. How many do I have here? 4. This is still possible if you have a 2x2 design. If you have some limits on how many trials or whatever these things refer to, you can do. If you have more higher factorial designs with more levels of factors, of course, to get a reasonable amount of data points within each cell gets harder. So 2x2 designs are, from my perspective, good designs for cognitive neuroscience. They're also being used quite a lot. They are relatively straightforward to think about, and they are also experimentally relatively straightforward to implement. For example, if you do that within subjects, and you have essentially 4 conditions, yeah. So each of these things you can of course also call condition 1, condition 2, condition 3, condition 4, and they represent these things.
It's just a typo. With the 1 and 3 on the left side. The 2 there's 2 is not, and 1 of them is factor 1 and 1 is factor 3. It's nothing major.
This is a 2.
Yeah, no, on the left side.
Ah, this one.
Yeah, nothing. Nothing important. Sorry.
Yeah, no, I wasn't just not looking. Yeah, so that's the second factor. Exactly. So this is the general outline of a two-way ANOVA, and as you rightly said, one can look at main effects of the factors and at interactions. In terms of in terms of the GLM version of these things, it depends on whether one actually models the interaction or one doesn't model the interaction. In terms of just computing group means and group standard deviations, what is commonly done, one way to visualize that is to again do bar graphs and do things like, okay, this is the average data from the combination of the first level of the first factor with the first level of the second factor. This could be the this would be the combination of the first level of the first factor with the second level of the second factor, and then this could be the outcomes of the or the averages of the combinations of the second level of the first factor with the first level of the second factor and the second levels of the first and the second factor. So in terms of main effects and interactions, what do we have in this case? Can somebody explain? Do we have a main effect of, maybe I should write this down so that it's clearer. So factor, so 1, 1 is factor 1, level 1. 1, 2 is factor 1, level 2. 2, 1 is factor no, does that, do I want it like this? Yeah, I want it like this. No, sorry, I'm doing, sorry, I'm completely confused. Sorry, that was of course not helpful. 1, 1 is level 1, level 1, that's what I want. And this is factor 1, factor 2. So the first number is the first factor, the second number is the second factor, and this is both level 1. This is level 1, level 2. This would be level 2, level 1, and 2, 2 would be level 2 of both factors. So now you observe this data pattern, and I'm asking you, is there a main effect of the first factor? Is there a main effect of the second factor? And is there an interaction? So who can explain? Maybe start.
Main effect of the first factor and interaction, and no main effect of the second factor.
Okay, so start with the first factor. So why do you think there's a main effect?
Because we see that that for all there is a main difference for there is a significant difference between.
Now, significance, I wouldn't say in this
Sorry,
sense.
there is a difference in the height of the bars between between the two level 1s and the two level 2s in corresponding to factor 1.
Yeah. So, one way to think about it is that, of course, this refers to the first level of factor 1. So you can, and this is one way to see it, you can average over the values of the factors of the second factor's levels. So you form the average of these two bars here, which is roughly here, and you can form the average of these two bars, and then you see that this for factor 1, level 1, is higher than for factor 1, level 2. And this is also the interpretation of main effects, so that it's averaged over the other factor. Okay, so somebody else with the second main effect. What can we say about this? And how do we get to it?
Could again take the average of the first and the third part, and the second and fourth part.
So then would so you said basically of this and this, which would be roughly here, let's say.
There is probably also an effect, but rather small.
Yeah, I would also say that it's smaller. Whether it's significant in the classical sense of significance, we don't know, because we don't really know what the variability is. But yeah. And in terms of the interaction, do we have an interaction?
Yeah, a small interaction, because explain this and describe this difference between the first two bars is smaller than the difference between the last two bars.
Yeah, that's exactly the way to explain this. So the difference here is essentially 0 almost, and here it's larger than 0, and interaction is a difference in differences. So this is exactly the way to interpret this. Good, very good. So you know what this means at this level. That's good. Now, to describe this from the perspective of the GLM, of course, we again want to create a model that models the main effects, and then later on also the main effects in the interactions. And this again requires that we adapt a little bit the notation of our data points and so on. So right now we had data points just being dots. Now we will call them y, j, k, and this is what we start with. So now these y, j, k are our values of the dependent variable, our outcome measures, our data points, however you want to call them. And I denotes the values of the levels of the first factor. So in general 1 to r, if you call actually the r makes more sense if you call this the row factor, so that would be then here factor 1. And this would be factor 2, because that's the column factor. The j, as I already mentioned, would be the column factor. So in general, you can have C levels of the column factor, and then within each cell, you would have a number of data points up to the number of data points you have in this combination, so Nij. In general, as I said, you want to have the same number of data points, so Nij would be the same for all values of I and j. And if we are dealing with a two-way ANOVA, and specifically a 2x2 ANOVA, then of course I is just going 1, 2, and doesn't go away, and j is also just going 1, 2, And then, for example, if you acquire 10 data points, so 40 data points in total, then this would be 1 to up to 10. Yeah, so that would be 10 data points in each of the cells, labeled as I and J. Now, what's the model for this in general? So again, in the GLM scenario, we assume that each of these data points results or is a realization of a random variable that has a normal distribution, a univariate normal distribution with a cell-specific expectation. Yeah, so that's cell-specific, and cell referring to the combinations of the levels of the factors, cell-specific expectation. And of course, the same variance parameter for all data points. Again, the assumption is that these cell and data point specific error contributions are all independent. It's fine. Sorry. Which then translates to a spherical covariance matrix. So they are all IID. Now, if we there are two ways to formulate GLMs for these kind of factorial designs. One is the additive way, and one is the way with interactions. So, who has used SPSS? Okay, so you might remember that if you go to GLM, if you do a 2x2 ANOVA, you go to sum of GLM, and then it says include all interactions, something like this. Remember that? Maybe not. So this basically, if you want to assess the interaction in your data with SPSS, you always have to tell SPSS, and of course you have to tell SPSS, that you actually want to model the interactions. And even if you don't remember that, you can model data from a 2x2 design without interactions or with interactions. You can model it in a million different ways, but two ways that we look at modeling data from a 2x2 factorial design is using an additive ANOVA design and then using an ANOVA design with interactions. And we start with the additive ANOVA design. And so there will be no interaction modeled, and there's also no way that you can assess interaction effects, and also that this model generates interaction effects. But it's helpful to get started on 2x2 ANOVA. So the basic additive ANOVA 2x2 design, so maybe we should call it additive 2x2 ANOVA. Models the cell-specific expectations, and this is like in the one-way case, of course, where the action is at the level of the cell-specific expectations, models them by means of an offset, a cell-specific effect of the first factor, and a cell-specific effect of the second factor. So don't confuse this now with the beta parameter. I just have beta here because I'm missing a beta label, and we had alpha before, so that's factor 1 effect for level I, and this is factor 2 effect for level J, where of course I and J go for level J, where I and J go from 1 to 2 for the 2x2 ANOVA. Yeah. And before the break, let me write this in terms of design matrix. So in terms of a design matrix, of course, the GLM design matrix formulation, we of course have to organize our data again. So we stack our data points in the different cells into one column vector, and of course we now have 4 different settings here. 1, 2, 2, 1, and 1, 2, y, 2, 2, 1, 2, y, 2, 2, and 2, 2. So this is just putting the data that that I presented here as dots into one column vector, and then our beta parameter vector for the 2x2 case, as it is formulated right now here, where I goes 1, 2, and j goes 1, 2. Our beta parameter vector looks like this. So we have 5 values in our beta parameter vector, which we use to again predict 4 expected values. So namely mu11, mu12, mu21, mu22. Of course, this is already over-parameterized, so we have to do something, but for the moment we do it like this. So now it's again the question how the design matrix looks, and any suggestions to get this model here, so this structural model based on these parameters for the expected values here. So we need mu11, mu11, to mu12, mu12, mu21, mu21, then mu22, mu22. So all of them obviously need mu0. So what would be the first column of the design matrix then? So in the design matrix, so that's our y, that's our mu, and now we write the design matrix, that's our beta. So we start with a column of 1s. Because if we then multiply this with our beta parameter vector here, then we definitely have the mu0 all the time. Now for mu11, we need which of the parameters here? Yep. That's true, but of course, yeah. So how would you do it? Let's say for mu11, yeah, we can. Naya, if you say we need.
would be 1, 0, 1, 0.
1, 0, 1, 0, yeah. 1, 0, exactly, and we need this for all the ones that are in mu11, and then
Then that one would be upper 1 and better 2, so that would be 1, 0, 2.
And somebody else for mu21 and mu22. Any suggestions? Oh, you go on.
That would be like adding 0, 1, 1, 0.
Yeah.
And the other one would be 0, 1, 0.
Exactly. So that would be the design matrix. Let me. That's better. That would be the design matrix corresponding to an additive 2x2 ANOVA design. No, it's not optimal. As you might be able to see is, again, if you add, for example, the third and the fourth column, you get the first column. So this is again a rank division matrix. Equivalently, if you think about generating these mu ij variables, so these expectations, 4 expectations based on 5 parameters, again, you can add a number to mu0, which is coming up all the time, and we subtract that from the remaining values. So again, it's over parameterized. So it needs to be something needs to be done to not have it over parameterized, and the way again is to do a reference cell reformulation by setting alpha 1 to 0 and beta 1 to 0. So basically what's going on in the first cell. So think about this like this, plus alpha 1. So currently it's in this format. So if these are our mu ij's for I going this way and j going this way, and now in the reference cell reformulation, the idea is to set these things here to 0. So to get rid of this and this, so that the expectation of the 1-1 combination of the factor levels is mu0. Also, because alpha 1 is 0, getting rid of this and getting rid of this. So that the interpretation of the remaining parameters is then again in terms of differences, but in an additive way. So if you go over the row factor like this, then you see that the additional effect or the difference between the first level and the second level of the row factor is given by alpha 2 and alpha 2 here. And if you go over the levels of the column factor, you see that the additional effect is in terms of beta 2. So there's no beta 2 here and there's no beta 2 here, but there is the beta 2. But you also see that regardless of the level of the other factor, there's always this additive effect. So if you're here, for example, at alpha 2, you get beta 2. So if you're at the second level of the row factor, so if you're here, you get beta 2. If you're at the first level of the row factor, you get beta 2. Yeah. So it's purely additive in the sense that there are no interactions, which is kind of a tautology, but nevertheless, I said it. In terms of the design matrix, alpha 1 and beta 1 are being deleted, and their corresponding columns. So we get rid of this. This column and of this column. And yeah, then we have this typical picture of a two-way ANOVA, which has ones here and then in the lower half, and then it has this way of including ones there. So that's kind of the typical ANOVA, two-way additive ANOVA form. Yeah. So let's have another break now, and then after that talk about 2x2 ANOVA with interaction. If there are no questions right now. No, good.